No, no.
Okay, actually, it's that time. So I'm going to go ahead and get started. We are going to continue balancing chemical reactions. As far as the homework is concerned, it has been brought to my attention that on some occasions it wanted the state of matter associated with it. Due to that, I will review the homeworks over the Thanksgiving break, and anybody that missed something strictly due to the state of matter, I will give you full credit for. So that is how I'm going to handle that, is to go through each assignment individually and edit accordingly. And because of that, I will not be assigning a homework due on Monday or Sunday, because it's going to be more of the same, where you would need to include the states of matter. And because of that, I'm not going to do that to you. I'm not going to cause that angst. So you will get 5 points for that. And I just wanted to let you know. Also, that means that I will write a quiz as soon as I get back to my office. The quiz will be due, though, on Sunday night instead of today. But it's going to be over the material that we went over on Monday, or that we would have gone over on Monday, which is more of conversions that we were doing. So it's not going to include balancing chemical reactions, again, because of the software I use and the fact that they wanted states of matter. So. The last thing I wanted to announce is I wanted to remind you that on Monday, we will all be meeting on Zoom. Today at 9 a.m., I believe it was, the folder for this week should have come, or for next week should have gone live. And the link to that Zoom is on that folder. So all you would have to do is go on to Blackboard, go to the folder and click on the link, and it should take you to Zoom. Any questions for me? Okay, so we're going to start out with a straightforward one, I hope. We've got potassium. First of all, I'm starting out with the unbalanced chemical reaction. I just review it and I don't see any polyatomic ions. So that means I am going to list out the elements. I have 1 potassium on the reactant side. I have 2 borons and I have 3 oxygens. On the product side, I have 2 potassiums. I have 1 oxygen and I have 1 boron. I personally I will say one thing that I typically do is I do start out with odd numbers. So if somebody has an odd number, I tend to start there. So I'm going to start with the oxygens and make the 2 sides equivalent. So on the reactant side, I have 3 oxygens. On the product side, I have 1. I need to multiply the product side through by 3. When I multiply whatever you multiply by becomes the coefficient of that reaction. When I multiply by 3, that means that I have 3 K2O molecules. So yes, I did get out 3 oxygens, 1 in each of the K2O molecules, but I also got 6 potassiums due to the 2 in each molecule. Now I'm going to go in and I'm balance out the potassiums. On the reactant side, I have 1. On the product side, I have 6. To make the 2 sides equivalent, I need to multiply the reactant side by 6. Whatever I multiply by becomes the coefficient. That gets me 6 potassiums. So now my potassiums and my oxygens are balanced. Now all I need to do is balance out the borons. On the reactant side, I have 2 borons. On the product side, I have 1. To make the 2 sides equivalent, I need to multiply the product side through by 2. Whatever you multiply by becomes the coefficient. And that is the balanced chemical equation for the reaction of potassium with diborotrioxide to form potassium oxide and boron. Questions? Okay. As I've said, for the most part, balancing chemical equations is a lot like a puzzle, but I am going to show you what I consider to be one of the more difficult types of puzzles, and that is going to be when we have to work with an alkane or a compound containing carbon and hydrogen, and we're combusting it. So let's take C6H6 and react that with oxygen to form CO2 and water. First thing I'm going to do is I'm going to just review it. And I don't see any polyatomic ions, so I'm just going to list out all my elements. So I have carbon, I have hydrogen, and I have oxygen. On the reactant side, I have 6 carbons, 6 hydrogens, and 2 oxygens. On the product side, I have 1 carbon, 2 hydrogens, and 3 oxygens. It is 3 oxygens because there are 2 oxygens coming from the carbon dioxide, and there is 1 oxygen coming from the water to make a total of 3. Questions? So now we're going to start balancing this reaction. One other rule that I didn't give you is another tip to balancing reactions is to save elements that exist in a compound by themselves until last to balance. The reason is you can use whatever coefficient necessary to balance that element as long as the reaction ends, or the balanced reaction consists of whole number coefficients when finished. Okay, we're going to use that tip. We could have used that tip in the last reaction as well, but we're definitely going to use that tip in this one. So what I noticed when I glance around at this reaction is oxygen is in a compound all by its little lonesome. So I'm going to save oxygen until last to balance. I'm going to balance out the carbon and I'm going to balance out the hydrogens first. So on the reactant side, I have 6 carbons. On the product side, I have 1. To make the product side have 6, I've got to multiply the product side through by 6. But when you multiply by 6, you get 6 CO2 molecules. So yes, you got 6 carbons, but now you have 12 oxygens from the CO2, giving you a total of 13 oxygens. 12 from the CO2 and 1 from the water. Now I'm going to balance out the hydrogen. On the reactant side, I have 6. On the product side, I have 2. To make the 2 sides equal, I've got to multiply the product side through by 3. Whatever I multiply by becomes the coefficient. So it gives me 3 water molecules. So I do get 6 hydrogens, but I also wind up with 3 oxygens. So now I have 15 oxygens. So my carbons are balanced, my hydrogens are balanced. Yes. What now? This number here? It was a 3. To make, oh, I see. To make 6, yes. Sorry. Yes.
I'm still confused on how you did the, like when you put the 6 in front of the CO2.
Okay, when I
did that.
What do you mean? How I did to get the 6 carbons, or?
Yeah, like when you turn the 3 into 13 and then 15.
Okay. So let's go back. Right now on that product side, when I put 6 CO2s in, I have 6 of these molecules. That's what that 6 out in front means, is you have 6 of those molecules. So that's where 12 oxygen atoms came from. When I went from 3 to 13, it's because at that time I had 6 CO2s, but I still only had 1 water, so that was only 1 oxygen. But by the time I was done, I had 3 water molecules, and so that meant I had 3 oxygens to add in, and so that's why we're at 15 now. Now, bless you. A balanced reaction, you got to have a balanced reaction. How am I going to get my oxygens balanced? I have 2 on the reactant side and I have 15 on the product side. What can I multiply by the reactant side to get 15? What can you multiply by 2 to get 15? Okay, 7.5 is an option here for now. That gives me 15. It's balanced, but there is a statement that you do have to pay attention to. And that is, we got to have whole number coefficients when we're done. There's a trick to this one. Right now, all the elements are balanced, correct? But I got to have whole numbers. I can't have a half. I can't have a fraction. So the trick to this one is I'm going to take the entire equation and multiply the entire equation through by 2. Even though it's not showing, there is a 1 here because we don't tend to show 1s. So 2 times 1 is 2 C6H6. 2 times 7.5 is 15 oxygens. 2 times 6 is 12 CO2s. 2 times 3 is 6 waters. And now what we have is we have the whole number coefficients we're required to have, and the reaction is balanced. Because we multiplied all the coefficients by the same value. Let's look at, yes.
Where did you get that 2 again? Did it come from?
It can be just, it's a multiplicative. It could be 3 if I needed to multiply a fraction by 3 in order to get it to a whole number. It's just to get a half to a whole number, you multiply by 2. Anything you need to use to get the fraction to a whole number is what you would use. Let's look at another example of another combustion reaction. We're going to go C4H10 plus O2 goes to form CO2 plus water. And I want to give you a chance to work on that one. So let's see how that one went. You have 4 carbon, 10 hydrogens, 2 oxygens on the reactant side. On the product side, you started with 1 carbon, 2 hydrogens, and 3 oxygens. We start by balancing out the carbon. To balance out the carbon, we need to multiply the product side through by 4. When you multiplied the product side through by 4, you got 4 carbons, but because that means you have 4 CO2s, it also means that you have 8 oxygens from the carbon dioxide and 1 oxygen from the from the water. We then balance out the hydrogen. On the reactant side, you had 10 hydrogens. On the product side, you have 2. To make this 2 sides equal, you've got to multiply through by 5. That means that we're going to have 5 water molecules. So yes, we did get our 10 hydrogens, but we also in the process wound up with 5 oxygens. So that means we are now at 13. This is that same type of process where we could have then multiplied the product side through by 6.5 to get 13, but we cannot keep it that way. We have to have whole number coefficients. So we would have multiplied the entire reaction through by 2. And when you do so, you get 2C4H10 plus 13O2 goes to form 8CO2 plus 10 waters. Any questions? Let's look at a different reaction. Not necessarily more difficult. I don't know. I'm just pulling one up. We're going to look at Ca3PO42 plus SiO2 plus carbon goes to form CaSiO3 plus CO plus phosphorus. The very first thing I do is I take a gander through this thing. And 2 things that I noticed. Number 1, yeah, I have phosphate on the reactant side, but I don't have phosphate on the product side. So unlike Wednesday, I'm going to have to break up phosphate this time. The second thing I noticed is that carbon appears in only one, appears by itself on the reactant side, and phosphorus appears by itself on the product side. So I may or may not save those. I initially my instinct would be to save them, but it may not be a possibility. So making our list, we have calcium, we have phosphorus, we have oxygen, we have silicon, and we have carbon. On the reactant side, you have 3 calcium, you have 2 phosphorus, you have 8 oxygens from the calcium phosphate, and 2 oxygens from the silicon dioxide for a total of 10 oxygens. We have 1 silicon and we have 1 carbon. On the product side, we have 1 calcium, we have 1 silicon, we have 3 oxygens from the calcium silicate, and 1 oxygen from the carbon monoxide for a total of 4 oxygens. We have 1 carbon and we have 1 phosphorus. This thing is not balanced. I'm going to start with the calcium. That seems the most logical. It may fall apart on me, but it seems the most logical. On the reactant side, I have 1 calcium. I have 3 calciums. On the product side, I have 1. To make the product side the same as the reactant side, I would need to multiply through by 3. But when I do so, that means I wind up with 3 calcium silicates. So yes, I did wind up with 3 calciums, but I also wound up with 3 silicons. And I wound up with, now I have 9 oxygens due to the calcium silicate and 1 due to the carbon monoxide. So that means I am now at 10 oxygens. Questions so far? The next thing I need to do is balance out the silicon. On the reactant side, I have 1. On the product side, I have 3. To make the product side the same, I'm going to have to multiply to make the reactant side the same, I've got to multiply by 3. But when in doing so, I wound up with 3 silicon dioxides. So I now have 8 oxygens from the calcium phosphate, and I have 6 oxygens from the silicon dioxide. So that's a total of 14 oxygens. Now, I'm going to balance out the oxygen next. I have 14 on the reactant side. I only have 10 on the product side. But I don't want to change that 9. I need 9 of them to stay just like they are. So if I have 14, but I need 9 of them to stay as they are, that means I need 5 to change. I need 5 from some other source. That other source is going to be the carbon monoxide, so that I wind up with my other 5 oxygens to give me a total of 5 oxygens from the carbon monoxide and 9 from the calcium silicate to make a total of 14. But that also made me have 5 carbons. On the reactant side, now I can balance out the phosphorus and the carbons. On the reactant side, I have 2 phosphorus. On the product side, I have 1. To get the same on both sides, I need to multiply the product side through by 2. And for the carbons on the reactant side, I have 1, and on the product side, I have 5. To make them the same, I have to multiply the reactant side by 5. And that is the balanced chemical equation. You will notice, though, I use the same rules. I use the same rule I used up here. I made sure to solve elements that appeared in a compound except for by itself. I saved phosphorus and carbon for last because they appeared in a compound by themselves. The new challenge, though, was the oxygen. And again, I didn't want to change the number of oxygens from the calcium silicate, because if I changed the oxygens from the calcium silicate, I would have changed the calcium, I would have changed the silicon, and I would have had to start all over again. So that's why I did this mathematics to figure out, okay, how many do I actually need from the other source of oxygen? Questions? Let me give you one to work on. Okay, I have 1 iron on the reactant side, 2 sulfur and 2 oxygen. On the product side, I have 2 iron, 1 sulfur, and 5 oxygens. First thing I'm going to do is balance out my iron. On the reactant side, I have 1. On the product side, I have 2. To balance them out, I would need to multiply the reactant side through by 2. Whatever you multiply by becomes the coefficient. But in getting 2 iron, I now have 4 sulfur. So I have 4 sulfur on the reactant side. I only have 1 on the product side. To make the 2 sides equal, I need to multiply the product side through by 4. Whatever you multiply by becomes the coefficient. But in getting 4 sulfurs, I now have 8 oxygens from the sulfur dioxide, and I have 3 oxygens from the iron 3 oxide. That makes a total of 11 oxygens. To get 11 oxygens out of 2, I would need to multiply the reactant side by 5.5. And so that's initially what I do. But you can't have a fraction. So to finish this out, we need to multiply the entire equation through by 2. When you do so, you're going to get 4 FeS2 plus 11 oxygens goes to make 2 Fe2O3 plus 8 sulfur dioxides. And that would be the balanced chemical equation. Questions? Let's do one more. NH3 plus O2 goes to form N2 plus H2O. And this is where remembering the rule I've already told you comes in handy. Which element would you suggest starting this balancing with? Nitrogen, hydrogen, or oxygen? Which one? I've got a nitrogen. I've got a hydrogen. Personally, I start with a hydrogen because oxygen is in a compound by itself on the reactant side, and nitrogen's in a compound by itself on the product side. The only one that's not in a compound by itself is the hydrogen, so I'm going to start with the hydrogen. On the reactant side, I have 3. On the product side, I have 2. To make these two sides equal, I'm going to have to multiply the reactant side by 2 and the product side by 3 to get 6 on both sides. Whatever you multiply by becomes the coefficient for that compound. So I wound up with 2 NH3s on the reactant side. That means I now have 2 nitrogens. And I wound up with 3 waters on the product side. So I now have 3 oxygens. Everything's balanced but the oxygen. Again, I'm going to throw a coefficient in here. I can put 1.5. And if I put 1.5, that's going to equal 3. But coefficients have to be whole number ratios, so I'm going to have to multiply the entire thing through by 2. And when you do so, the reaction is 4 NH3 plus 3 O2s go to 2 N2s plus 6 H2O. And that is the balanced chemical equation. Questions? Okay, with that, like I said, I will see you on Zoom on Monday. Otherwise, enjoy your holiday. I think we've all earned one.
What's the biggest that those can be?
When I do I mean, I don't know. When you burn octane, you get 25 oxygens. So, I mean, I frequently do a reaction that requires 25 oxygens, but I imagine it can go much larger. It depends upon the complexity of the molecule. If you do something with DNA and RNA, it's going to get much bigger.
Interesting to see how far some of